Hi, my name is Greg Mead. I am a faculty member at Santa Fe College in Gainesville, Florida. And this lecture, it's going to be a very brief discussion, is intended to show you how to calculate relative humidity. This seems to be a real problem for some of my students. And so before we get into that, I want to talk about what humidity itself actually is. So when you think about water vapor, are you talking about mist, fog, clouds, all of these, none of these? Let's click on this and see if we can get the answer to that. And think about this. When you're driving through fog or mist, windshield gets wet. Why is that? It's because fog and mist, and also if they're off the ground, clouds are generally not water vapor, they are liquid water. Water vapor is a gas. People often talk about water vapor as if it's the thing that you see coming off of a pond when it gets cold, or as if it's clouds. Whenever you see it, it cannot be water vapor. Water vapor, by definition, is a gas. If you can see it, it's not a gas. Mist and fog are liquid water. Most clouds, things like this, are liquid water. The only exception to clouds not being liquid water are very high clouds, such as cirrus clouds, and these are dust-sized ice crystals. They're very small, but they're not gas. Again, if you can see it, it's not water vapor. It's either solid or liquid water. So that's the thing to remember when we're talking about water vapor. When we're talking about humidity, we're talking about the amount of water vapor as a gas that's present within the atmosphere. So let's get away from this and go look at the different terms that we use when we are discussing water vapor. The first thing you need to think about is the amount of water vapor actually present in the atmosphere. This is the amount of measurable water vapor. There's a number of different ways to measure this. We can talk about it as mixing ratio, specific humidity, absolute humidity, vapor pressure, and these are the definitions of those. I won't go into them in detail. You can read them, they're right there. We are going to be using specific humidity, but it doesn't matter which one of these. You can use any one of these to talk about the actual amount of water vapor in the atmosphere. They use slightly different units. And we can use any one of these to calculate relative humidity as well, as long as we're consistent in the units that we use. So the specific humidity, which is what we're going to use in this video, is the amount of water vapor, and remember, water vapor is gas, the amount of water vapor in grams of water per kilogram of air. And again, it's present as water vapor. Now, there is a maximum amount of water vapor that's possible to have in the atmosphere, and that is called saturation. And it's expressed very similarly to the amount of water vapor actually present. We can call it the saturation mixing ratio, the saturation specific humidity, and this is what we're going to be using, the saturation absolute humidity, or the saturation vapor pressure. And again, they're defined slightly differently. What we want to look at is the ratio of the actual amount versus the saturation amount. Now, how do we get these things? Well, the actual amount, which again is this right here, these have to be measured. You have to measure the actual grams of water present in the atmosphere in various volumes, either in kilograms of air or in cubic meters of air. You can measure in pressure. It doesn't matter how you do it. This has to be measured. Generally speaking, when you're calculating relative humidity, unless you're a professional, you are not going to be asked to measure the actual amount of water vapor. That is something that will have to be given to you, presented to you in a problem. If you're asked to calculate relative humidity, you're going to be given one of these values. And again, we're going to be using the specific humidity. On the other hand, the saturation humidity, which is right here, is a function of temperature. The warmer it is, the more water molecules you can have in the atmosphere as water vapor. And these values have been measured, the maximum values have been measured. And again, we're going to be looking at the saturation specific humidity. This right here is a graph of the saturation specific humidity. And notice that temperature is on this axis. This is in Celsius degrees. So 0 degrees, that's freezing. Increases, the saturation specific humidity increases as temperature increases. Think of it this way. The higher the temperature, the faster the molecules are moving around, and the more molecules can be evaporated into the atmosphere at higher temperatures. So this graph is a graphical way of looking at this table. Notice at 40 degrees Celsius right here, the saturation specific humidity is 47 grams of water per kilogram of air. So what do we mean by the term relative humidity? The relative humidity is the ratio of the amount of water vapor you actually have in the atmosphere versus the maximum amount you can have. If the maximum amount you can have is, say, 40 grams of water and per kilogram of air, and the amount that you actually have is 20 grams of water per kilogram of air, then you are halfway to saturation. And so you would say your relative humidity is 50%. So how do we make this calculation? Well, if you have a saturation humidity of 20 grams of water per kilogram of air, and you have a saturation specific humidity of 40 grams of water, and remember water vapor, not liquid water, per kilogram of air, your relative humidity is equal to the saturation humidity divided by the saturation specific, the specific humidity divided by the saturation specific humidity. And we always express this in percent, so we multiply it by 100% to get that 100 in. And in this case, this would be equal to 20 grams of water per kilogram of air divided by 40 grams of water per kilogram of air times 100%. I want to show you a few things to notice about this. First of all, notice that grams of water per kilogram of air is present both in the numerator and the denominator of this ratio. And you know that when you have the same thing in the numerator and the denominator, that can cancel out. That's not only true for numbers, that's true for units as well. And it's very important to put the units in because it will help prevent you from making mistakes. So we put them in there, but now we can cancel that out and cancel that out. And because we have zeros here in the top and bottom, 20 and 40, we can actually be lazy and cancel those out as well. And so we've reduced this whole big thing to 2 over 4. And I think most of you can figure out 2 over 4 is 1/2. And then the next thing to notice is that we have the times 100 to turn this into a percentage. And this, the whole thing will simplify to 2 over 4 times 100%. And that's 1/2. So 1/2 of 100 is 50%. And that's the relative humidity if we start with these numbers. Okay? So I want to go through a few examples of this to help you understand how to make these calculations and what will happen if conditions change. So when we look, oops. So when we look at our graph, if we want to use a particular specific humidity, we're going to just have to look at these numbers, and whatever it is whatever it is. That is, again, something that's going to have to be given to you in the problem. On the other hand, if you're asked to figure out what the saturation specific humidity is at a given temperature, the way to read that is to go to whatever temperature you're asked about and then go up to this graph and then go over. If it's an even 5 degrees, you can go to one of these and you can actually just read off from the table. That's the easiest way to do it. So, for instance, if we were asked what is the saturation specific humidity at 25 degrees Celsius, 25 degrees Celsius is right here, we would go straight up to where our vertical line crosses the graph, and then we would go over and we would find that our saturation specific humidity at 25 degrees is 20 grams of water per kilogram of air. Okay. If we were asked what is the saturation specific humidity at some other temperature, say at 32 degrees Celsius. Here's 30, there's 35, 32 is going to be a little bit this side of halfway, and we would go as nearly as we can straight up, and we might encounter the line right here. We would then go straight over, and we would see that the saturation specific humidity at 32 degrees Celsius is, it looks like it's about 29 grams of water per kilogram of air. If you did it a little bit more carefully, if you actually, say, used a ruler, and we did something like this, you could even measure it, measure that distance if you wanted. You might find that it was maybe closer to 30 degrees. If it's not right on one of the values of an even 5 degrees, you'll have to estimate. And there's nothing wrong with that. Do the best you can when you make that estimate. Get the best measurement you can for the value that you're dealing with. This right here, if it was there, it would be 30 degrees Celsius. Okay? So that's how you're going to make those estimates. So let's start just picking some numbers out of the air. I'm sorry to give you a bad pun like that. But let's suppose, for instance, that we have a temperature of 30 degrees Celsius. At 30 degrees Celsius, we can either go up to that, or we can look over here at 30 degrees Celsius, and we find that our saturation humidity is 26.5 grams of water per kilogram of air. And remember that your humidities, whether it's saturation specific or just your specific humidity, will always have the units of grams of water per kilogram of air. And so at 30 degrees, the saturation specific humidity is going to be 26.5, again, grams of water per kilogram of air. Let's imagine that we actually have 18 grams of water per kilogram of air present. The specific humidity, which again is the actual amount of water present, will be 18 grams of water per kilogram of air. So our relative humidity, again, and it's a good idea, especially as you're learning how to do this, to always write out the equation for relative humidity. Relative humidity equals saturation humidity divided by this, specific humidity divided by saturation specific humidity times 100. And now that you've got that written out, you can write in the actual numbers. And so the specific humidity is 18 grams of water per kilogram of air divided by 26.5 grams of water. I'm writing this wrong, sorry. Grams of water per kilogram air times 100%. And again, we can see that the units will cancel out, which indicates to us that we're writing this correctly. And that would be equal to 18 over 26.5, and the units are all gone, times 100%. And you can't see it, but I just brought up the calculator. So if we type in 18 divided by 26.5, we get that number. And then if we multiply that by 100, we get a relative humidity of 67.9%. And so our relative humidity under those conditions is 67.9%. Okay? Let's do another example, and we'll try to keep the calculator clear. And I'm just coming up with these numbers off the top of my head. If we start with a temperature of, say, 20 degrees Celsius, we can go up here and we can look at this, and it's a little bit lower than halfway. It's probably about 14 grams of water per kilogram of air, maybe 13.5. We can go over here and we can cheat, go up to 20, go over to 14. So in fact, it is at 20 degrees. the saturation specific humidity is 14 grams of water per kilogram of air. If we have previously measured and have found that the actual amount, the specific humidity, is 10 grams of water per kilogram of air, then our relative humidity, again, is the specific humidity divided by the saturation specific humidity times 100%, which will be 10 grams of water per kilogram of air divided by 14 grams of water per kilogram of air times 100%. And again, we can cancel out the units, which gives us confidence that we are doing this right. And that will give us 10 divided by 14 times 100%. And 10 divided by 14 times 100 gives us a relative humidity of 71.4%. So I hope you can see that we're doing this in exactly the same way every time. Find out what the specific humidity is, write it down. Specific humidity in this case is 10 grams of water per kilogram of air. Find out what the temperature you're at is. Then from that, read either from the graph or from the table what the saturation specific humidity is. Write that out. Write out your equation, then put your numbers in, and you'll get the answer. Now, the interesting thing that happens is that because saturation specific humidity changes with temperature, if you have a certain specific humidity and a changing temperature, your relative humidity will change even though the amount of water present in the atmosphere is constant. So let's take a look at this. Let's do some investigation into what happens. Suppose we start with a temperature, to make it a convenient number, suppose we start with a temperature of 25 degrees Celsius. If our temperature starts at 25 degrees Celsius, that means that our saturation humidity is 20 grams of water per kilogram of air. So the saturation specific humidity is 20 grams of water per kilogram of air. Let's imagine that we start with a specific humidity of 10 grams of water per kilogram of air. So again, this is going to have to be something that's given to us. If we start with 10 grams of water per kilogram of air actually present in the atmosphere, then I think it's going to be fairly easy to make this calculation. Our relative humidity is going to be 10 grams of water per kilogram of air divided by 20 grams of water per kilogram of air times 100%. And 10 over 20 is, again, we're going to cancel out the units. So 10 over 20 is 1/2. 1/2 of 100 is going to be 50%, and we can even avoid using the calculator for that. But now, let's imagine that in the middle of the day, our temperature is 20 grams of water per kilogram of air. And then, as the day gets older and older, as the sun goes down, the temperature drops. And let's imagine that the temperature drops from 25 degrees down to 20 degrees. If the temperature drops down to 20 degrees, then our saturation humidity decreases to 14 grams of water per kilogram of air. So that means that this number, which is the saturation specific humidity, is now going to be 14. And this will be 14. And that means we will have to recalculate our relative humidity. The relative humidity will now be 10 grams of water per kilogram of air divided by 14 grams of water per kilogram of air times 100. That gives us 71.4%. So simply by changing the temperature, we haven't changed the amount of water in the atmosphere, we've just changed the saturation humidity, and we've increased the relative humidity from 50% to roughly 71%. If we decrease the temperature down farther to 15 degrees, notice that our saturation specific humidity at 15 degrees is now 10 grams of water. So at 15 degrees, and I'll put it in a different color, at 15 degrees, our saturation specific humidity is now 10 grams of water per kilogram of air. And that means that, again, we have to redo these numbers. And we now have 10 grams of water per kilogram of air for the saturation specific humidity. And 10 over 10, obviously, is 1 times 100. Our saturation, or rather our relative humidity, is increased to 100%. We cannot have a relative humidity greater than 100%. The saturation specific humidity is, by definition, the maximum amount of water you can have evaporated into the atmosphere. This leaves us with an odd problem. What's the problem? The problem comes up if we decrease temperature even farther. So at 10 degrees, our saturation specific humidity is 7 grams of water per kilogram of air. So at 10 degrees Celsius, the saturation specific humidity is 10 grams, is 7 grams of water per kilogram of air. But a moment ago, our specific humidity was 10 grams of water per kilogram of air. And of course, if the maximum that you have, which is what the saturation value is, if the maximum is 7, you can't have 10. So what has to happen? Something has to give. And what happens is that when you drop below 10 grams, when the saturation specific humidity drops below 10 grams of water per kilogram of air, water starts to condense, water vapor starts to condense out of the atmosphere until it equals the maximum that you can have. And so what happens is that the specific humidity drops to 7 grams of water per kilogram of air. And that means that your relative humidity now equals 7 grams of water. Well, let's do it this way. Equals the specific humidity divided by the saturation specific humidity, of course, times 100%. And that means it equals 7 grams of water per kilogram of air divided by 7 grams of water per kilogram, H2O, per kilogram of air times 100%, which of course equals 100%. So once the temperature drops enough so that the saturation specific humidity equals the specific humidity, you start getting condensation if the temperature continues to drop. And so at 15 degrees, we were at 100% humidity. As the temperature continues to drop, the specific humidity will follow the saturation specific humidity, and as long as the temperature continues to drop, our specific humidity will continue to drop, and we will remain at 100%. This temperature, the temperature at which our saturation specific humidity equals the specific humidity, is the temperature at which condensation begins, and this temperature is known as the dew point. And you'll notice that the time of day that you usually get fog occurring is in the late evening. And the reason for that is as the temperature decreases, eventually the temperature reaches the dew point, and at that point you begin to get condensation. And as long as the temperature continues to decrease, you will continue to get condensation and you will get fog. The next morning, as the temperature starts to increase, you'll get above the dew point, and in fact what will happen is that the fog will evaporate. We often call that process burning off of fog, but of course it's not really burning, the fog is just evaporating and it disappears as the day goes on. And so this is how you make calculations of relative humidity from the specific humidity, which you have to know through some other means, and what that means is that somehow meteorologists will actually measure the actual specific humidity, and then you use the saturation specific humidity to figure out what the maximum is, and then you just get a ratio of the two to get your relative humidity. If you make a calculation and your relative humidity is greater than 100, that's impossible. And what that means is that you have made a mistake, and so you want to check your numbers again. Okay, well, good luck. If you have any additional questions on this, please contact me through Zoom or through email or come to my office. Okay.